When we think of a machine breaking down, we usually picture um, a dramatic explosion.
Right, or a gear just snapping in half.
Exactly. It's loud, it's obvious.
Yeah.
But welcome to the deep dive, because today we are looking at something completely different.
Yeah, in the bleeding edge of precision mechanical engineering, the real battles are actually invisible.
Right. We are looking at an atomic level war against friction, wear, and extreme physical environments. So for you listening, our mission today is to unpack how engineers manipulate materials to survive conditions that would, well, instantly destroy standard metals.
And you have to start right at the surface. I mean, before you completely replace a machine's core material to survive a harsh environment, your first line of defense is just altering its skin.
Okay, so how do they do that?
Well, one of the primary surface treatments for things like circular splines is diamond-like carbon coating, or DLC.
Diamond-like carbon.
Exactly. It's this amorphous carbon film that creates a barrier with literally diamond-like hardness and, incredibly low friction.
So it's basically like applying an indestructible non-stick armor to a frying pan.
Yeah, that's a great way to put it. The friction just glides right off.
And that low friction is, it's absolutely critical for clean room environments, right?
Oh, absolutely. Because in those spaces, you can't use traditional liquid lubricants.
Right, they would contaminate the whole manufacturing area.
Exactly. So DLC allows the gears to run perfectly under dry friction, which is just unlubricated friction.
Wow, and that extends the time between maintenance shutdowns significantly?
It does. But, engineers are always pushing further.
Which brings me to my next question. If you have this ultimate wear-resistant shell with DLC, why is there also this massive focus on nitriding? It seems totally redundant to alter the surface a second way if the DLC armor works so well.
It sounds redundant, yeah, but nitriding, specifically plasma nitriding, operates on a completely different physical principle.
Okay, how so?
Well, a coating like DLC, it just sits on top. Under enough stress, it can theoretically peel and flake off.
Oh, I see.
But nitriding actually chemically alters the base metal itself. You are infusing nitrogen atoms directly into the surface.
Wait, so the atoms wedge themselves into the metal?
Right. They wedge between the iron atoms and lock the crystalline structure in place.
So it's not like painting over a brick wall. It's more like injecting hardened mortar right into the pores of the bricks.
Exactly. It pushes the surface hardness to over 600 HV, which is almost double that of standard untreated steel.
That is wild.
Uh-huh.
But doesn't heating the metal up to change it mess with its shape?
That's the beauty of plasma nitriding. It's a relatively low temperature process.
Wow.
So it avoids warping the part. You gain this massive fatigue strength, but you don't sacrifice dimensional stability to thermal distortion.
But sometimes altering the surface just isn't enough, right? When the operating environment itself is intensely hostile or weight is a critical barrier, you eventually just have to throw out the steel core entirely.
Yeah, you do. And that is where engineers move to entirely different base materials, like the titanium alloy flex spline.
Right, and the specific alloy they use a lot is Ti6Al4V, which blends titanium with aluminum and vanadium.
Correct. And that combination gives you a metal with only 60% of the density of steel, plus it's completely impervious to saltwater corrosion.
Which basically makes it the holy grail for underwater exploration robots.
Oh, for sure. You can maintain the high power density you need for deep sea pressure, but you shed the weight and completely eliminate the rust problem.
But I'd imagine making these precision flex splines out of titanium is an absolute nightmare on the manufacturing floor.
It is notorious. Titanium's toughness means it aggressively wears down cutting tools, so machining is incredibly difficult.
I bet.
Plus, its fatigue properties are fundamentally different from steel. You basically have to do a complete redesign of how the drive handles mechanical stress over millions of cycles.
So since metal is clearly becoming the bottleneck here, the logical next leap is just throwing metal out altogether.
Right, and that leads us to the composite flex splines that are currently in R&D.
Like carbon fiber reinforced polymers or CFRP.
Exactly. They use CFRP to drop the weight even further. But beyond just losing weight, composites offer something that metals really can't.
Which is?
Incredibly high damping properties. You see, high-speed harmonic transmissions inherently generate acoustic noise, but composites actually absorb those vibrations.
So it's basically like using a carbon fiber tennis racket to absorb the thwack of a ball preventing that impact shock from vibrating up your arm.
That is exactly how it works. But, whether you are damping vibrations with composites or reinforcing the surface with nitrogen, there is still an ultimate enemy under heavy loads.
Galling resistance.
Yes, galling.
For you listening, galling is what happens when two pieces of metal slide against each other under immense pressure.
Right. The friction causes them to essentially weld together at a microscopic level.
And then violently tear apart, right?
Exactly. It's the primary cause of sudden, catastrophic seizure in high-torque environments.
So how do they stop that from happening?
To prevent galling, flex blinds rely on specialized stainless steel formulations. They are specifically chosen for their high galling resistance.
So when an unexpected high torque spike hits the system, the material itself is designed to survive that micro tearing.
Right, so the drive doesn't just lock up instantly.
It's an ongoing battle against physics. Engineers are constantly forced to push boundaries, from the atomic structure of the surface to the fundamental composition of the core.
They really are. The materials have to be as sophisticated as the robots they operate inside of.
It really leaves you wondering about the future for you and these machines. I mean, if carbon fiber composites eventually eliminate all acoustic noise and advanced atomic surface treatments completely eradicate friction and wear, what happens next?
Yeah, will future mechanical drives become entirely maintenance-free?
Exactly. Could the joints of a robot actually outlast the robot itself? It's definitely something to think about next time you see a machine in motion.